interested in is computational structures in Hilbert space. So that's kind of a vaguely defined term. So let's see what this could mean. So I'm interested in quantum computation and quantum algorithms, and in such a situation, we are asking a classical question. We expect a classical answer to this question, but the processing in between can be quantum. So that is my set. Yeah. Classical answers is what we can understand. Classical questions is what we can ask. So I have two criteria here for what a computational structure in Hilbert space is. So it must specify an input structure, it must specify an output structure, and the function computes. And nonetheless, there must be some quantumness in it and a proof of that. So that is my set of criteria. So are there such things at all? I forgot to say something. So why am I asking this question at all? So, well, the long-term direction for this is that we are interested in maybe finding novel quantum algorithms. So maybe this gives a new perspective, first for classifying quantum algorithms, and then maybe picking the interesting ones among this classification. So that's the long-term perspective, but let's begin at the beginning. And this is the start. It's the first example of what, under those criteria, would qualify as a computational structure. So this is Mermin's star. So it's definitely quantum, and this is revealed by its contextuality. So Mermin's star is invoked in a contextuality proof. But then it was shown a couple of years ago by Jeanette Anders and then Brown that this Mermin's star here computes. You can actually repurpose it as a little quantum computation. And this was mentioned a couple of times before in this conference, and I will actually go through it in some detail. So this is the simplest example of the kind that I'm interested in. And we have a bunch of examples like this. And what we now want to do, and that is the purpose of this talk, to find commonalities in all these examples that we have and build the framework for them. So what I will be going to do is I'll put two links together that already exist. So there is the link between quantum computation and contextuality, and this comes in two varieties. So there is the Mark Howard and Company link that is for quantum computation with magic state, and then there's the link by Anders and Brown, which is for measurement-based quantum computation, and I will be talking about the latter. So this talk will be about measurement-based quantum computation. So that's link number one. And the other link is by Abramsky and co-workers, and it is between contextuality and cohomology. So I have been at an earlier conference, earlier edition of QPL, that was in 2011, and this is what I took home from it and wanted to make something of it, and now it's 2016. What can I say about that? So, at any rate, so we will not be using the mathematics that is used here, so that's Czech cohomology, and we will be using group cohomology, but, well, it's just another variant. So we ask what happens if we put those two links together, and you already see the structures that we will be describing will cohomological, and because of this link, we get a cohomological description of contextuality, and we will also get a cohomological description of computation. Okay, so here's the results that I want to at least mention. I will not be able to show them all. So the first is that I want to introduce this cohomological framework for you. So there's a central notion in it. It's a so-called phase function, and it has a history. It has previously appeared in Fourier-space crystallography, if there's any condensed matter physicist here in the audience. At any rate, the phase function is the central object in this description. And it is a one-chain in group cohomology, and this is where cohomology begins. So, and then from the viewpoint of computation, so this one chain contains the function that's being computed in the quantum computation. It also contains the witness of contextuality, namely if its co-boundary doesn't vanish, this is a witness for contextuality, as we shall see. So this is pretty much what I expect to be able to do in my talk. For cohomological picture, this isn't quite enough. I mean, if I say cohomological picture, you want to see cohomology groups appearing. And that does indeed happen. So these measurement-based quantum computations that I talk about, they will be classifiable by a certain second cohomology group. But I can only mention it. Another thing that I will mention right now, because I think I will not be able to get back to it, is, so this is kind of a familiar connection, so that people want to do. You want to identify a resource for quantum computation, in this case contextuality, and then you want to establish it as a precondition for speedup. So that has previously been done for entanglement, most notably for the circuit model by Giffrey-Vidal, and then by Martin van den Ness and collaborators for measurement-based quantum computation. Has recently been done for Wigner function negativity by the group in Sydney. And here we have a similar result for contextuality. So every measurement-based quantum computation of the kind we describe, for every such computation there is a non-contextuality inequality. And only if this non-contextuality inequality can be violated by a large amount, only then you can have positive speedup. But I will be focusing on the first part. So here's an outline. So I have a review part. I will briefly talk about measurement-based quantum computation and contextuality, and I'll do this all in the example of Anders and Brown, and the example of Merman-Stark. Then I will make a slight twist to measurement-based quantum computation. I will introduce its cohomological formulation and then talk about its ramifications. So let's get started. So here comes the review part. I don't want to say too much about it. I think you've seen this slide before. In measurement-based quantum computation, the computation is driven by projective measurement as opposed to unitaries. And that's all I'm going to say. So it's computationally equivalent to the circuit model. Contextuality of quantum mechanics versus non-contextual hidden variable models has also appeared before, so I want to be brief about it. So let me just say this. A non-contextual hidden variable model is something of the following kind. So you have your physical system, and you could imagine it having a catalog attached, and this catalog lists all the observables that can be measured and already contains the values that are being outputted if this observable is being measured. And so the outcome here depends only on the observable being measured. That's a non-contextuality assumption, not what could be measured in conjunction. So that's a non-contextual hidden variable model, and the question is, can it exist? So the Cauchy-Specker theorem tells us that in dimension, Hilbert space dimension greater or equal to 3, such models fail to reproduce the predictions of quantum mechanics. So they can be ruled out, and that's called contextuality of quantum mechanics, because non-contextual hidden variable models fail. Okay, so let's see this in the example of Merman square. I just want to talk a little bit about it because it's of interest for our computational connection. So what you see here is 10 observables on a 3-qubit Hilbert space that are arranged in a certain pattern. So what are the observables? So we have the Pauli spin flip operator sigma x on the first qubit, Pauli spin flip operator on the third qubit, and so on and so forth. So if you look on each line, you will find that these observables are commute pairwise, and furthermore, their product is always plus or minus the identity. So if you want to build this catalog of these predetermined measurement outcomes, this relation that I just mentioned leads to a consistency condition. Namely, if the product of the observables was plus the identity, the values have to multiply to plus 1. Similarly, like in this horizontal context, if the observables multiply to minus the identity, the values have to multiply to minus 1. So that's that. Then you have the further constraint because the eigenvalues of these observables are plus minus 1. These values also have to be plus minus 1 only. And now you can write down a system of 5 equations and easily check that it does not have a solution. These equations are contradicting each other. So there is no such catalog for this example. There is no consistent value assignment. that was one of Merman's proof of the quotient spectral theorem. For reasons that I don't want to go into, he proposed a state-dependent version of this very same argument. So he introduced a state, Greenberger-Horn-Zeilinger state, which was just the joint eigenstate of these observables. So these observables now have values, and they're just the eigenvalues of the corresponding stabilizer operators with respect to that state. Okay, so now they have values, and you can now repeat the game. Still, you find no consistent assignment because the problem didn't get any easier than it was before. But this is now our jumping board to talk about computation. So this is the setting of Onlus and Brown's measurement-based computation. So I don't want to go into too much detail, but just want to tell you how the computation works, because that's how all the computations are going to work in our setting. So one context is taken up by a state, so 4 contexts remain for measurement. And these 4 contexts can therefore be labeled by 2 bits. And this is our input to the computation. So the input to the computation chooses a context. So then, what the computation does, it measures these local observables, and from its outcomes, it infers the outcome of the product observable, which is of course deterministic, since it's an eigenvalue of the state that's present. And in this way, you can easily convince yourself that this computation produces an OR gate. And that isn't very much in absolute terms, of course, but it was important for the scheme, as was discussed earlier today, because it promotes the classical control computer present here to classical universality. Okay, and it works only because we have contextuality in the setting. So this is the end of my review part. So now we begin changing the setting slightly. So, yeah, so there's a slight modification that I will apply to the setting of measurement-based quantum computation, and this is explained on this slide. So this introduces the notion of the input group, and that's why I'll call it GMBQC, and I'll say in a moment why this change is made. So here is how group elements become input in the computation. So the input group G has the property of mapping the set of measurable observables to itself. So what's happening, how you relate a measurement context to an input is as follows. So there is a reference context, C of E here, that is associated with the identity in the group. And then all other contexts are obtained from this reference context by conjugation under a group element. And so a group element is assigned to each measurement context. Okay? So let's summarize what we have in the general setting. I mean, using this figure here for the Merman star, but it's general. So in the computation that we are interested in, all observables that play a role, measured observables and the inferred observables, they have all eigenvalues plus or minus 1 only, but they don't have to be Pauli observables. We have the input provided by a group, and therefore the function that's being outputted is from the group to the binary numbers. Okay. So now let me say why I do this, why this modification. So there is a reason why you cannot just assume that your possible inputs form a set. If you assume nothing beyond that, then you have a lot of freedom in assigning inputs to measurement contexts. And that's actually something that's not desirable, because it gives you a lot of computational power without using any quantum resources. So you can basically construct, you can basically compute every Boolean function without ever using significant quantum resources. So that would not be a good model. So we need some specialization, and we are putting this specialization in the form of a group. We're putting a group structure here, and the reason we do that is because that contains the former case of standard measurement-based quantum computation as a special case. Okay. Another thing that I need to point out, all I say is for temporarily flat measurement-based quantum computation. So measurement bases do not depend on measurement outcomes obtained elsewhere. And that is a very substantial restriction, and it's not a good thing, but that's all I can handle at the moment. Okay, so let's go to the cohomological framework and let's introduce the phase function. I need to, phase function is introduced here, but before I go to that, I need to introduce a little bit of notation. So we have already encountered two types of observables. That's really all that matters here. So there is the observables that are potentially being measured in course of the computation. And then there's this other type of observables that's responsible for the output. I mean, this is whose eigenvalues will be inferred by measuring these other observables. So that's the only observables that appear in the scheme. So first, the measurable observables, the local ones in this picture, we collectively denote by the set O plus. And then those and the inferable observables together, we denote by the letter omega plus. And for that set, we have index set A. Okay, just as a notation that I need to introduce. So now, we haven't talked about the resource state yet in the general case. So we had one resource state in this specific example. It was the GHZ case. But in the general case, we require that our resource state rho satisfies these symmetry conditions. And let's just go through what these are. So what we have on the left is just any of the expectation values of these observables with respect to the resource state. On the other side, we have the expectation value of another observable that's obtained from the former by conjugation. And in between, we have a phase factor plus minus 1. So we require this symmetry condition, which means that in the orbit of any such observable under the group, the expectation values differ only by plus minus 1 phase factors. And these plus minus 1 phase factors, they are specified by the phase function that's going to be our central object. We need to talk a little bit about whether this is a meaningful constraint to put in place. So we can immediately check that it is obeyed in the GHZ case. Well, that's because for everything that's not in this context here, the expectation values are 0 and the equation is trivially obeyed. And then, well, this is deterministic quantum computation, so all these eigenvalues are plus minus, all the expectation values are all plus minus 1. So sure, you can find a phase function that matches them. Okay, but that's not the only case. I mean, there's a broad class of resource states that match this condition. So when our resource state is a stabilizer state and the success probability of the computation is uniform, then this condition is satisfied. So there is some basis for enforcing. Okay, so we need to talk a little bit more about this phase function. So the phase function has two arguments. So it takes one argument here in the group and another argument here in the index set that is describing the observable. And so let's talk about this thing a little bit more formally. So more formally, this phase function is a one cochain in group cohomology. So here is where the cohomological picture starts. So it is a function from the group G into a module V. And this module V, I have not described yet. It's a module of functions on the index set of observables. This is how you would evaluate it. And okay, so let's just quickly say what it means. So let's do this in the example of Mermanstock. So we could think of flipping these observables. I mean, take some observable and map it onto minus itself. And we want to do this in such a fashion that the product constraints all remain intact. They don't change sign. So this would be an example. So we can check each context is affected by an even number of sign flips, so it doesn't change. Okay? That would be an example for such a function. And if you have two such functions, then their product or sum is also a valid function, and that's why you get this module structure. Okay, so this is how these two arguments, A and G, come into play for the phase function. And the important thing is that it's a one function. So let's now talk about the ramifications. There's two things to talk about. We have to talk about how the phase function contains information about what's being computed and how it is related to contextuality. Okay, so here is how the phase function is related to computation. So, so we do this in the deterministic case because that's easier to verify. So we're talking now about these observables here. And so since it's deterministic quantum computation, in this case the expectation values for all these observables are plus and minus 1. So we can write this by minus 1 to the power of the value of the outputted function for that group element. And so you just insert this into the symmetry condition that we have enforced on the resource state, and you find that the outputted function is related to the phase function in this fashion. So the outputted function evaluated for some group element is equal to the phase function evaluated for that group element, and then at a particular location in the set A plus an offset. And this offset does not depend on the group element. So this means that the phase function contains the outputted function modulo a constant offset, relative constant. Okay, so that basically takes off our requirement number 1, that our topological structure should tell us what is being computed. Okay, so that was that. And the other item is contextuality. So we want to know which phase functions are compatible with non-contextual hidden variable models and which ones are not. And so we have the following proposition. So for every measurement-based quantum computation of the kind that we are interested in, if for all phase functions that satisfy the output relation that we just talked about, it holds that the co-boundary of the phase function doesn't vanish, then this computation is contextual. So here is more cohomological structure, so we are computing co-boundaries. So let's talk about what the co-boundary of a one cochain is and how it enters kind of the physics of this scenario. So yeah, so recall that we had this symmetry condition here, and it holds for all group elements. Since it holds for all group elements, we could in particular look at product of group elements, and then we have a consistency condition of the group modification. So this product group element applied to this element of the index set is the same as first doing this multiplication and then this multiplication. Okay? And well, that's just compatibility. And we plug this into the symmetry condition, and we get this relation. So which relation? So we see on the left and the right of this equation, we have the same expectation value decorated with different phase factors. So this equation can be satisfied in two ways. It can either the expectation value is 0, that indeed happens, we've seen that before, or this combination of phase functions is 0. So either of those two can happen, and the latter thing can be written, but that's just a definition of the co-boundary of the phase function. So that can again be written in a cohomological fashion. So just as a remark, for you to see where this is heading, so in the quantum mechanical case, so sometimes this happens, sometimes this happens. But if you have a phase function that's compatible with a non-contextual hidden variable model, you always require this. So if you find that this doesn't happen or is not possible, then you know that's a contradiction with the contextual hidden variable. And that's what I'm going to show you on the next slide. So here we have the proposition again, and here is the proof, and that's really all it is. So let me just read again what the proposition was. So for any measurement-based quantum computation of this kind, if the phase function, if all phase functions that satisfy the output relation have a non-vanishing coboundary, then the computation is contextual. So that's what we want to show. And the proof flips this whole thing around. So it starts with assume a non-contextual hidden variable model exists. If that's the case, well, then you need at least one consistent value assignment. And if you have that, you can construct a phase function, phi s, on it. And here's the definition of it. Yeah, it's just the addition modulo 2 of two evaluations of the value assignment at different locations. And then you can just do two things. You take this and check that it satisfies the output relation, and it satisfies that its coboundary vanishes. So yeah. So this means whenever you have a hidden variable model, you have a phase function that satisfies both, which is equivalent to this statement. Okay. So that takes off the second requirement, namely that the phase function have a proof or witness of contextuality in them. Okay. So yeah, so my time is up. So let me just mention what this is before I go to my conclusion. So this proposition here doesn't tell you that a particular setting is contextual. It only says if these conditions are satisfied, then the setting is contextual. Now you want to work with this. You want to apply it to certain settings. I mean, you want to do something with this formalism. So you might want to apply it to the Mermin star. And this would be the proof that Mermin star is indeed contextual in this notation. So, I mean, there's too much to go through here in 30 seconds, but you see at the end, this is 1 versus 0 contradictions. Very similar to Mermin's original parity argument, except that this is now invoking a symmetry condition. I'm not going to go through it, it's just an advertisement. If you're interested in this version of the proof, I'd be happy to go through it with you. Okay, so let me just go right to the conclusions. So this is really what I was able to go through here in my talk. So this is the cohomological description of measurement-based quantum computation. We have a topological object, the phase function. It has information about the function that's being computed in the MBQC, and it provides a witness for contextuality and hence quantumness. So that's what I talked about. Again, the rest is advertisements. So, well, there is a contextuality inequality that gives you an upper bound on hardness of classical simulation, and these measurement-based computations are classifiable by the second-order cohomology group. Open questions. So I proceed here from the special, more short-term to the more general. So as I said, this is only about temporally flat computation. That is kind of unsatisfactory. We want to have the full story also covering the temporally ordered case. Second point. Do I have? Yeah? So second point. Group cohomology has entered measurement-based quantum computation in a different way. So this is this business of symmetry-protected topological order, computational phases of matter. And there, these computational phases of matter are also classified by certain second-order cohomology groups of groups, second-order group cohomology. And so there's a very strong connection at the formal level. But is there also, I mean, is this accidental or is there a physical connection? I don't know. Finally, the broadest question, is there a kind of a paradigm for quantum computation that relates to contextuality in the same way as quantum parallelism relates to superposition and interference? Thank you.
I think we can entertain a couple of questions.
So everything you were talking about was mod 2, right? Over Z 2.
Mm-hmm.
Could it be generalized to other rings? I've asked you this.
Shall we have a bet? What shall we bet about? A beer? I say it's the same.
So you think it all will generalize?
I think it
and
will.
then you get
I mean,
similar results for working over
Yeah.
well, appropriate kinds of qubits or...
yeah, I think it does. It doesn't make a difference.
Right.
I mean, I'd be happy to have this scrutinized, but at this moment I cannot see where it would fail.
So in the usual MBQC, the temporally flat ones are computationally quite weak, right?
Yeah.
Is it linear time simulable or something like this?
I wonder where you take that statement. I mean, there's Dan Brown's work, or essentially Dan Brown's work, where they related to the boson sampling problem. So there is temporarily flat MBQCs that are super hard. I mean, however, this argument doesn't apply here. So these, I believe, are fairly straightforwardly simulatable. I'm not sure linear. I don't think so. But they are not very complicated. So yes, in this scenario, I think temporal order matters for computational complexity.
I was wondering if, looking at the group for which you're building your context, whether this gives you some more fine-grained analysis of the basement of complexity.
When I change the input group here, yeah, I do not have examples. Other than, I mean, you can make this some arbitrary finite non-abelian group. I don't have any good examples for that.
I think we better table further questions, but let's think.